In this lesson, we will discuss support vector machines, or SVMs, one of the foundational machine learning algorithms for classification. We will start with the problem formulation and introduce the idea of max margin classifiers. After that, we will go over linear SVMs with a focus on theory and geometry, then move to kernel methods to address nonlinear classification. Finally, we will discuss how to extend SVM to multiclass problems, then touch a little bit on scalability and list a few applications. Let's start with a simple classification example, such as classifying movie reviews as positive or negative. Each review can be represented as feature vector x1, x2, x3, such as the number of times the word awesome appears, the word disappointing appears, and so on. The label in this case is whether the review is positive or negative. In mathematical terms, x is a multi-dimensional feature vector, y is a positive or negative label, and our goal here is to correctly label input examples. The key idea behind support vector machines in a simple two-class classification problem is to find a linear separator for the data. In this example, we have the same data set with two separator lines, h1 and h2. The natural question is which line is doing a better job? Now, just looking at the accuracy of prediction in the training dataset is not going to add any insights because both lines are achieving 100%. All the blue are separated from red here, and all the blue are separated from red in H2. So what else can we consider? SVM looks at the distance between the decision boundary and the nearest points from each class. This is called the margin. So if we take H1, the nearest point from the two classes seems to be farther away, which is creating a larger margin in comparison with H2, which has a smaller margin. So with all being equal, we prefer the line with a larger margin because this gives us more confidence in the separation. In other words, this idea of maximizing the margin is exactly where the notion of confidence in SVM comes from. Then, of course, there's an extension for this idea to nonlinear predictors. So instead of a straight line, we get curves that separate two classes. But the principle is the same. We still look at how far the closest points from each class are from the decision boundary, which is the margin that we aim to maximize. Now we are able to break down the linearly separable case. So a separating hyperplane can be written as W transpose X plus B equals 0, where W is the weight vector, B is scalar. In the two-dimensional case, this can be written explicitly as Wx1 plus W2x2 plus B equals to 0, which defines the decision boundary between the two classes. Let's work through the two sides of the equation. Suppose we plug a point x1, x2 into this equation and get a positive value. The point lies on one side of the hyperplane. Let's say it lies on the h1 side. Similarly, if the value is negative, the point lies on the other side of the hyperplane. So the sign of f of x determines the predicted class. So this is basic operator. But SVMs go one step further. Let's focus on the margins. We need a separator with the largest margin between the two classes. So formally, all the trailing point must lie outside or on these margins or dotted boundaries. Two questions that always come up. First, why multiplying by yi? And what's the thing about greater than or equal 1, less than or equal minus 1, or sometimes it shows up as another value? For the first question, multiplying by yi is just a common trick to guarantee that the correct prediction has the same sign as the true label. But for this greater than equal 1 and less than or equal minus 1 ensures that the point lies beyond the margin boundary, not just barely correct. Note that points can still show up inside the margin, but we have to track those points, which make the support vectors. The points that lie exactly on H1 or H2 are called support vectors. They are the most critical points because moving them would change the boundary. Other points further away do not matter for defining the separator. Suppose we have the equation of a line which is given by a of x plus b of y plus c equals to 0, and a data point like x0, y0 somewhere in the plane. A natural question from coordinate geometry is, what is the distance from this point to the line? And as we may already know, it's given by this formula, which is the absolute value of ax of 0 plus by of 0 plus c over the distance square root of a squared plus b squared. Let's further break down this equation. So the numerator measures how far the point is from satisfying the equation of the line, and the denominator ensures that the distance is independent of how we write the equation of the line. Now in SVMs, instead of having a simple line equation, we have something more general like f of x equals w transpose x plus w0. The signed distance formula becomes as yi f of x of I over the norm of w. As you can see, the distance matters a lot in SVMs because the goal is to find the hyperplane that maximizes the margin, which is the distance between the boundary and the nearest points on each side. And as you can see in this max-min formulation, we're trying to find W and B that maximizes the minimum distance to the hyperplane. A couple of notes about simplifying the linearly separable formulation. First, we set up the minimum of yi f of x of I to a constant such as 1, and instead of solving for argmax wb 1 over the norm of w, we find argmin wb for the norm of w squared. And once we do that, the final formulation becomes finding argmin wb for the norm of w squared subject to yi f of x of I greater than or equal to 1. What we have here is a constraint optimization problem where we can use a quadratic program to solve it and get the parameter models that we need. Now let's move to the general case when the data are not perfectly separable. If you look at this example, we still have the same data set, but notice there are a few red points and blue points crossed into the margin region where they're not supposed to be. So if some points violate the margin, we can't keep the constraints as before because it's going to make the problem formulation infeasible to solve. So the key idea to deal with this case is by introducing a slack variable denoted by xi that keeps a track for these violations. For these light red points and light blue points, the value of xi I equals to 0 because these points are on the right side of the margin and also outside the margin boundary. So there is no violation and no action needed. Now let's pay attention to what's going on inside the boundaries. For this dark red point, the value of xi I is somewhere between 0 and 1 because it crossed the margin boundary, but it's still in the right side of the line. On the other hand, this dark blue point or dark red point, it crossed to the opposite side where it should not be, so the value of xi I is greater than 1. Now back to the mathematical formulation, and as you would expect, we need to sum over xi I and add it to the formulation and seek to minimize this slack variable value. One more important detail, the formulation still tries to maximize the margin while minimizing the total penalty, and in order to achieve this goal, it introduces a control variable to capture this trade-off. And when C is multiplied by the total of the penalty, when C is small, which means it allows for more mistakes in the boundaries. And when C is larger, that means less mistakes are allowed. And this soft margin SVM is widely used and adopted. Lastly, we want to look at how the effect of this control variable for smaller c's or larger c's. Let's see what's going on here when c equals to 0.001, which is a very tiny value, which means we're not being penalized for violations. The margin is very wide, but as the value of c increases to 0.05, then 1, then 10, you can see how the margin shrinks because now the model is giving more priority to the correct separation over the width of the margin. And it's a good time to remind you that C is a hyperparameter, which means it needs to be tuned for each problem to balance the margin size and classification accuracy. Moving on, let's discuss the nonlinear extension of SVMs using the classic XOR problem as an example. As you can see, we have two variables x1, x2 in the original two-dimensional space, but there is no straight line that can separate the red points and the blue points. One solution is, instead of staying in the original two-dimensional space, map the data into a higher dimensional feature space using a function like phi of x, and then try to fit a linear SVM in that space. Then this linear separator in the higher dimensional space corresponds to a non-linear boundary in the two-dimensional space. Let's see how this plays out in this example. x1, x2 are transformed into 6 features. Let's say z1 equals x1 squared, z2 equal x2 squared, z3 x1 x2, z4 x1, z5 x2, and z6 equals to 1. And as you can see, we were able to find a linear hyperspace in the higher dimensional space that separated the red and the blue points, which corresponded to the nonlinear curve in the two-dimensional space. So to summarize, this mapping phi of x is where the power of nonlinear SVMs come from. In practice, we can't keep manually figuring out what that mapping should be for each problem. It quickly becomes messy and impractical. To address this problem in SVMs, notice how the algorithm only relies on inner products between transformed data points, which we can get from a kernel function. So in mathematical terms, a kernel function k of xi comma xj equals to phi x of I, phi x of j. In other words, this kernel function allows computing these inner products in the high-dimensional space without explicitly doing the mapping. And there are several common choices for kernels. It depends what is the nature of the feature space we are working with. For polynomial problems, the polynomial kernel expands features into higher order polynomials. For example, suppose we want to map our data into a quadratic features space. We can do that by using the polynomial kernel with h equals 2. The Gaussian radial basis is used for infinite dimensional feature space, and the sigmoid function resembles the activation function from neural networks. So far, we discussed SVM with two-class classification problems. Still, SVMs can be generalized to solve multi-class classification problems. One approach is one versus rest, which means for each class, we train a classifier that separates that class from all others combined, which means for n classes, they're going to be n classifiers. Then at prediction time, we evaluate all classifiers and assign the class with the strongest response. Another approach is called one versus one, which instead of comparing one class against others, we train a classifier for every possible pair of classes, but this is going to result in a large number of classifiers, but higher accuracy. Then at prediction time, each classifier votes, and the class with the majority vote is chosen. Is SVM scalable to massive datasets? The answer is yes, but it depends on the setting. Remember that the key property of SVMs is that complexity of the trained classifier is not determined by the dimensionality of the data, but by the number of support vectors. In other words, if only a smaller fraction of the data becomes support vectors, then the model can generalize very well in high-dimensional spaces. In summary, linear SVMs are highly scalable and efficient, whereas kernel SVMs can be powerful in some setups, but their scalability is limited, and it depends on the number of support vectors and the optimization of the solver. On the application side, SVM can be used to solve many two-class and multi-class classification problems. To name a few applications: object recognition, speaker identification, and computational biology. And final word on SVM, it has elegant mathematical formulation, it guarantees a global optimal with optimization, it trains very well on a small data set, but at the same time, there are challenges with large data sets. Performance can be slow, and representation is restricted to map linear models.